Imagine sitting inside a metal capsule, hurtling toward Earth at 17,000 miles per hour. The temperature outside your window hits 3,000 degrees Fahrenheit. That's hotter than lava. And yet you survive. How? Welcome to TinyButWise, where we take the small things you ignore every day and reveal the big truths hiding inside them. And today we're diving into one of the most dramatic moments in all of space exploration, the moment a spacecraft comes home. But before we get into that, let me ask you something. Have you ever stuck your hand out of a car window at highway speed and felt that rush of air pushing against your palm? Now imagine that force, but multiplied by 1,000. That's what a spacecraft feels when it enters Earth's atmosphere. So here's what I want you to think about. Why doesn't it just burn up completely? Why do some things burn and others don't? And here's the one that really gets me. What if the engineers got it even slightly wrong? What happens then? Hold on to that last question. We'll come back to it. And trust me, the answer will change the way you think about space travel forever. Let's start from the beginning. When a spacecraft finishes its mission in orbit, it doesn't just fall straight down like a ball you drop from a rooftop. It's moving sideways at an almost unimaginable speed. Think about the International Space Station. It travels at roughly 17,500 miles per hour. That's fast enough to circle the entire Earth in about 90 minutes. Now, to come home, it has to slow down. And slowing down means diving into the atmosphere. And diving into the atmosphere at that speed means one thing: heat. Enormous, violent, terrifying heat. Here's where it gets fascinating. Most people assume the heat comes from friction, like rubbing your hands together really fast. But that's actually a myth. The real reason a spacecraft heats up so dramatically is compression. As the spacecraft screams downward, it slams into air molecules so fast that those molecules don't even have time to get out of the way. They get compressed, squeezed together. And when gas gets compressed that quickly, it generates extreme heat. We're talking temperatures that can reach 3,000 degrees on the surface of the spacecraft. For reference, steel melts at around 2,500 degrees. So yes, without protection, the spacecraft would simply cease to exist. Now here's where human engineering becomes almost miraculous. Scientists and engineers figured out that the key to surviving reentry isn't making something that can withstand that heat forever. It's about managing it, controlling where the heat goes and how long it lasts. And they came up with solutions so clever, they almost seem like cheating. The first big solution is called a heat shield, and the genius of it is almost poetic. Instead of blocking the heat shield absorbs it and then slowly burns away, taking the heat with it. This is called ablative shielding. Think of it like an ice cube protecting your drink. The ice melts so the drink stays cold. The heat shield sacrifices itself so the astronauts inside stay safe. NASA used this exact approach on the Apollo missions. When those capsules came screaming back from the moon, the heat shield on the bottom burned and vaporized layer by layer, releasing that energy safely into the air around it. But wait, here's something even wilder. The shape of the spacecraft matters just as much as the material. You might think a sleek, pointy rocket shape would cut through the air and reduce heat. Logical, right? Wrong. It turns out a blunt, rounded shape actually works better for reentry. A blunt shape pushes the shock wave of compressed air slightly forward, away from the spacecraft. This creates a small gap between the hottest air and the surface of the vehicle. The shock wave does the heavy lifting, and the spacecraft rides behind it like it's using the heat as a shield. Engineers call this the blunt body theory, and it was one of the most counterintuitive discoveries in aerospace history. Now think about the Space Shuttle. That was a completely different animal. Unlike the Apollo capsule, the shuttle was designed to land like an airplane and be reused. So you couldn't have a heat shield that burned away every time. Engineers needed something that could handle reentry over and over again. Their solution? Ceramic tiles. About 24,000 of them, covering the belly and leading edges of the shuttle. These tiles were made from a special silica material that was such a poor conductor of heat, you could hold one end with your bare hand while the other end glowed red hot. That is not an exaggeration. NASA actually demonstrated this on camera. The tile looked like it was on fire, and a technician held it barehanded on the other side. Each tile was custom-shaped to fit a specific spot on the shuttle. No two were exactly alike, and every single one had to be inspected and sometimes replaced before each flight. It was painstaking, expensive, and time-consuming, but it worked. For 30 years and 135 missions, the Space Shuttle used those tiles to come home safely, most of the time. This is the part where we have to talk about what happens when something goes wrong. Because on February 1st, 2003, the Space Shuttle Columbia broke apart during reentry. Not in space, during reentry. 16 days into the mission, during launch, a piece of foam had broken off and struck the leading edge of the left wing, damaging the thermal protection tiles there. The damage seemed minor. Engineers debated it. Some were concerned. Leadership decided it was likely okay. It wasn't. When Columbia hit the atmosphere, superheated air rushed into that damaged wing and tore the spacecraft apart from inside. All 7 crew members were lost. It remains one of the most heartbreaking reminders that in space travel, the margin for error is razor thin. Getting it slightly wrong doesn't mean a bumpy ride. It means everything. That tragedy reshaped NASA's entire safety culture, and it also pushed engineers harder to develop better, more reliable reentry systems for the future. Fast forward to today, and the new generation of spacecraft is doing something remarkable. SpaceX's Dragon capsule, the same one that carries astronauts to and from the International Space Station, uses a modern heat shield made from a material called Pica X. It's a carbon fiber-based ablative material that SpaceX actually developed and patented themselves. It's lighter than older materials, incredibly effective, and can handle multiple reentries with minimal replacement. And yes, the Crew Capsule Dragon has already brought astronauts home safely multiple times, splashing down in the Atlantic and Pacific Oceans. But here's the twist that blew my mind. When we talk about reentry, we usually imagine coming back from orbit. But what about coming back from deep space? From the Moon or even Mars? The speeds are even higher. An Apollo capsule returning from the Moon entered the atmosphere at nearly 25,000 miles per hour, far faster than an orbital return. The heat generated was proportionally more intense. And engineers had to calculate the re-entry angle with stunning precision. Too steep, and the spacecraft would burn up. Too shallow, and it would skip off the atmosphere like a stone skipping off water and get lost in space forever. The window was just a few degrees wide. A few degrees. That's the difference between coming home and disappearing forever into the void. And that's really the point of all of this. Surviving re-entry is not one thing. It's a perfect combination of shape, material, speed, angle, and timing, all working together. Change any one of those variables even slightly, and the outcome changes completely. The engineers who figured this out weren't just solving a math problem. They were playing with fire. Literally. The next time you watch a rocket launch or see footage of a capsule streaking through the sky wrapped in a blazing orange glow, remember what's actually happening. Inside that inferno, human beings are trusting their lives to ceramic tiles, ablative shields, and a blunt piece of metal aimed at a window just a few degrees wide. And somehow it works. That's the magic of engineering. That's the audacity of human beings deciding that space is worth the risk. What do you think? Would you get into that capsule knowing all of this? Let me know in the comments. If you found this video valuable and learned something new, do us a favor, like subscribe to TinyButWise and share it with your loved ones. Now your turn. Drop a comment with the next topic. We read every comment, and the best suggestion gets a shout out. See you there.